welcome back, and today we're right back onto the FFC card. I have absolutely no idea where this episode is gonna go. It's pretty much sitting exactly like how we left it in the previous episode, which was we got the operating system ready for the FFC card. Now, I've been doing a lot of work off camera trying to get a feel for what's going on and where our faults might lie. So that way, when I turned the camera on today, I actually had a direction to run in. And I've learned some interesting things. First of all, in the previous episode, when I did the seek test that we found on the Hawk drive, I told it to go from track 00 to track 2F, and a lot of people commented that potentially the floppy doesn't have that many tracks. We've actually confirmed that the floppies have 4 C tracks. So I didn't tell it to seek beyond the number of tracks that it had. I think maybe I just had a bad connection on the floppy cable there. When I film these, I plug things in and unplug them countless times to try and get all of the different shots, and I think I just maybe didn't have it plugged in right. But we'll give that another test today. I'll spin up the Hawk drive and give that another test, make sure the seek test is working correctly on that drive, and then if it is, we'll continue on with troubleshooting on the FFC, because like I said, I think I have an idea of where to start looking, and I have some really good tools to help me start doing that today. So we're gonna take a look at all of that, and oh man, I hope that we can get it working. I am cautiously optimistic. I'm not optimistic. Well, I don't know what I'm saying. This thing's been kicking my butt 6 ways to Sunday, but we're not going to give up on it, so we'll try to get it going as best as we can. So let's hop over there and get started. All right, we're right back where we left off. The only thing that's changed from the previous episode is that I've removed drive B here. It was just kind of in the way for making sure that everything on drive A was working correctly, because it was so close up there that I couldn't really see the head or anything moving back and forth. And let's run the same seek test that we did last time that failed. Last time I did low track 00 to high track 2F. This time I'm going to go the full distance. I'm going to go 00 to 4C. So I've got the Hawk drive spun up. We're in the flexible disk diagnostic up here. So we'll do the seek test. Our unit number is 0. Our seek pattern is U. Low track is 00. High track is 4C. Printer is 0. It loaded the head. I can see it seeking the head all the way out. And there it goes. It did a successful RTZ back to track 00. So it didn't just run into the stop at the end and just sit there hammering on it like it did last time. So most likely I just had a bad ribbon cable connection. There was a bunch of stuff going on trying to get all that stuff filmed. I must have just missed it. But it looks like the seek test is working perfectly on the Hawk drive. So the next step is to try to figure out why it won't pass the read test. And to do that, I need to start probing things on the FFC card itself. And in order to do that, I need some new tools. So let me bring the camera over to the bench and show you some really cool stuff that I recently got. So I was saying that I thought I may have had a bad connection on the ribbon cable that was causing it to not pass the seek test correctly. And that could have been due to a couple of things. One, this adapter that I have here is not the best made thing in the world. I did get this PCB backwards. I wanted the jumpers to be on the inside. And the part that plugs into the back of the floppy here is actually a little too wide and it doesn't plug in all the way. So I definitely needed to make a revision 2 of this. I'm really glad that I made this one because I learned a bunch about it, and that made making revision 2 a lot easier. And well, I'll just go ahead and show you revision 2 here. And you may notice that there is some surprising differences between the two. Revision 2 is considerably smaller. It is etched, and it is dual-sided. And that's interesting because it's obviously not machined, which means I didn't make the PCBs for this one. And in fact, they were made by PCBWay. PCBWay reached out to me. They were really interested in the channel, interested in the types of things that I was doing, and they asked if there was any way in which they could help. And there was some PCBs that I actually had to order from a PCB manufacturing company. So, well, I took them up on their offer, and you can see that I actually have 3 different single-sided PCBs, and then I have 1 dual-sided PCB here, and this is just changing the pinout of the floppy to match the pinout of the FFC card. And well, you may notice that there is no silk screen and no solder mask, and that was actually intentional. I really wanted to see what PCBWay's manufacturing looked like without a silkscreen or solder mask. You don't see PCBs made like this much anymore. I particularly love this look because it's very reminiscent of the types of PCBs that I cut on the mill, but also I have a project coming up in the future that I'm gonna need to order PCBs for, but I want them to look exactly like this. So I'm actually really happy with how these came out. So thank you so much for this PCBWay, but that's not the only thing that you guys made for me, is it? And this is a Centurion riser board. It's probably the simplest board you could make, although I somehow still managed to mess up. I'll point that out here in a second. But all it does is it takes the pins that are on the bus and moves them over to a connector that is on the edge that allows me to essentially move the card that I want to test all the way out into the open to make it easy to probe. Also, I really wanted a silkscreen on here to point out what the known signals were that were pulling off of the backplane in the bus there. So that makes a huge difference. And well, I also bought these little ejector clips off of Mauser that work beautifully. But again, PCBWay hooked me up with this, and aside from my mistake, which I don't know how I did that. I was so obsessed with trying to get the solder mask correct on these edge connectors here that somehow I deleted the bottom ground line here and didn't notice it until like 3 days after I placed the order. So unfortunately the card is only going to be getting its ground through the top rail here, but that's on both sides, and I've actually tested this out and it seems to work just fine without our bottom ground rail here. But PCBWay, thank you so much for making these. There's gonna be a revision 2 order coming in soon, so I'm gonna put that little ground rail back on there. But I think it's time to put this board to use, because this is gonna let me put the FFC clean out of the system so I can start probing on it. All right, let's get the riser card in place, and we're gonna use it on the FFC card here. So I'm gonna unplug the main ribbon cable here. This is the DMA cable, so we'll get it out of the way. We'll pop the FFC card out. Slide our riser card in. And then we'll connect the FFC card into the edge connector of the riser card. And now I need something to support the FFC card. So I've got some Centurion manuals here that I'm just gonna slip right underneath there. That'll hold that FFC card up. And then, well, now that is a new and interesting problem. We don't have a DMA cable that's long enough. Even if I disconnect it from the Hawk drive controller, that's still too short. So we're gonna need a new DMA cable. So I've got this cable here, which I think came from the Phoenix drive. I don't really know, but it's got the same pinout as the DMA cable. So I can plug it in directly here, and then I can plug it into the FFC card over here, and that'll get our DMA working. But now I can't use the Hawk drive because this cable only has 2 connectors on it, and I would need a 3rd connector to plug into the Hawk drive. So we have to think of a new solution for that. And SJ Software, or Gecko, coming in absolute clutch yet again here. If I slide the diag card out, you may notice that there is a new ROM in the F3 slot, because he wrote a brand new F3 ROM for me with an RTZ test, a format test, and a clear error test. So we've got 3 brand new tests on the diag card here that should allow us to really exercise the floppy drive without having to spin up the Hawk. And let's give the FFC card here a quick test with the riser card just to make sure that everything is working. The floppy's on, the computer's on with the FFC card hanging way out here in the open. So let's start with a known good test, 08, which is the floppy seek test. So if I do 08, hit enter, the head loaded and I can see it's doing the seek. So I'll go ahead and log the control C. Now we just gotta sit here and wait for it to seek all the way out and all the way back in. All right, that passed perfectly, so we'll go ahead and hit space. Next is a format floppy test. And this is less of a test and more of a utility, actually. It's gonna format the floppy for use with the Centurion. Let's format this floppy by doing 06 here. Hit enter, it loads the head, and now it is very slowly going through every single track, formatting it for the Centurion. We can see we get a nice little blinking lights display on the front panel here. It successfully formatted the floppy. Of course, that doesn't mean anything because we can't actually read the floppy. And well, the first thing that we need to check is that if after it fails a read test and it says busy, did not clear, what kind of loop does it go into? But the only way to know for sure is to actually read what the microcode is doing on the FFC card. And that's going to require yet another very special tool. This is an HP 1630D logic analyzer, and it was donated to the channel by an absolute rock star, John, who has a wicked collection of vacuum tubes and old test equipment, and he said it was just sitting there and needed to be put to good use. And it has definitely been put to good use, but it's going to come in extremely handy for checking out the FFC card, because I want to get a look at the microcode addresses and see what addresses it's sitting in when it's failing the read test. And this piece of equipment can make that possible. So imagine an oscilloscope that allows you to look at dozens and dozens of signals at once. Of course, it's not quite like that. An oscilloscope is allowing you to look at the actual signal, see what kind of shape it has, see what kind of rise time and fall time it has. A logic analyzer boils that down to a 0 or a 1, a logic low or a logic high, which is totally fine if we're looking at digital signals and we don't need to see the integrity of those signals. We just need to see their values. And John, you absolute legend, thank you so much for donating this to the channel. I'm going to put it to use right now, and let's take a look at what the address on the FFC is looking like. We're all set up. The logic analyzer is on, showing me the address of the FFC card, which is also currently on. The Centurion's on. We're sitting in the auxiliary tests menus, and the microcode address while sitting in idle seems to be cycling from 2B5, 2B6 to 2B8 and then back. So next, let's take a look at what the microcode address does when we do a seek test. The floppy drive is seeking, and it looks like we're at an address of 2B2, an occasional 2B1, and 2B5 or 2B6. Either way, the floppy is seeking successfully out. It's now coming all the way back. The test finished, and now we're back to our 2B5, 2B6, and 2B8 loop. So next, let's do the test that fails, the read test. It looks like we're at an address of 303 and 304 alternating. So that's our tight loop. That's the loop that we're stuck in. So we know that while the FFC is stuck in its tight failure loop, the microcode is cycling between address 303 and 304 hexadecimal. So I've written down the microcode that's at each one of those addresses, and what do I do? What do I do with this information? First of all, what is microcode? I'm still kind of learning my way through microcode, and it's easiest for me to understand if I just think about one single ROM. A ROM is a read-only memory. We program it once, you throw it in the system, and it's a source of constant data. We throw an address at it, and we know that a certain 8 bits are going to come out of it. And microcode is exactly that. Only instead of those 8 bits being some data value that is important for doing math or something like that, those 8 bits are now just control lines for different pieces of hardware on the circuit board. Microcode is code to control the hardware directly. And well, there's more than just one ROM chip on the FFC card. There's actually 8 ROM chips on there, which means that there are 64 individual control lines snaking throughout the entire system, controlling other pieces of hardware. So if we know what addresses we're stuck at, we can follow those 64 individual control lines to find out what pieces of hardware are being turned on or modified or changed in certain ways. So for example, address 303 and 304, H1 is outputting the value of 08. And this means that those 8 control signals, 7 of them are low for both of them, 1 of them is high for both of those addresses. If we look at H2, it outputs 7F at 303 and FF at 304. That means that that 8th bit is changing depending on which address we're at. So that is a changing signal that is part of our loop. And that is just 16 signals of the 64 total control signals that are going throughout the system. Not only is it very difficult to wrap your head around, you absolutely have to have a schematic. But thankfully, Meisaka is an absolute legend and she reverse engineered a full schematic for the FFC, and that's where Gecko and SJ Software has been spending his time lately, looking at and understanding the microcode. He says that when it's in the read test, it's kind of just stuck in this loop looking for the composite data coming from the floppy drive. And even after it says busy did not clear, it stays in this loop. So this is really good news because it means that we can essentially just do a read test, let it get stuck in the loop, and then we can start probing around on the FFC card itself, looking for that data. Time to get the oscilloscope out and start probing. So we're gonna have an oscilloscope, a logic analyzer, a riser board. We're doing a lot of specialized stuff in this one, but hey, we're getting there. We're gonna figure out what's wrong with the FFC.
And I hit a fault almost immediately. That was unexpected. I made a whole list of the data input pins on the FFC here, starting from the connector, going pretty much as deep as I felt comfortable tracing out on the schematic. If I start at the connector here, I should be seeing the data coming from the floppy drive into the FFC. And I am on J1 pin 2, but pin 1 and 2 are tied together. So both of these pins should have some form of data showing up on them. And well, the scope is just totally dead, completely flat. There is no data whatsoever coming in through the connector. So it could be that we don't have any data coming out of the floppy drive. So we need to move up there and start tracing it all the way back to the read head and find out if we're losing it somewhere along the way. All right, I think I've got another bad chip on this board here, and I think it's this 339 up here in the top left, U1. If we look at U1, it has an inverting input and a non-inverting input, which are also both directly connected to test point 1 and test point 2. And so if I put my probe on test point 2 here, I can see that there is something happening on that test point. So there is some data going into that pin, same with test point 1. So we have inputs coming into the 339. Now this should amplify them greatly and put a big signal out on pins 7 and 12. So if I check pin 7 here, it is totally dead. There is nothing coming out of it. It looks like it's sitting at about 1.5 volts, which doesn't seem right. There should be absolutely something coming out of this 339, and it doesn't appear to be doing that. So I'm gonna pull that one out, put a socket in, and replace it with a new 339 and give this another test.
All right, it's been a couple of days, not a smooth couple of days. We've kind of run headfirst into a bit of a problem. But before we even get that far, we had to make sure that we were getting good data into the floppy drive and good data out of the floppy drive. And it turns out that U1 was pretty much just continually giving us problems. It is an LM319, and I pulled the only two other 319s that I had off of the PCB for drive B, and both of those were bad. So I cut up a little adapter PCB that adapted that pinout to half of an LM339. And that's what's sitting in the board right now. And then we used the riser board to take a look at some of the timing signals, because we were pretty sure that we were having a timing problem. And there is a VCO on the FFC card that you can control the timing of with a little variable capacitor. And we got it adjusted to exactly what the microcode is expecting, which was on the pin we were checking 1 megahertz. So the VCO is adjusted perfectly. We put the FFC card back in, and well, now we've got a new problem, and I'll demonstrate it for you. So if I just do the RTZ test that SJ Software built into the diag card here, that is test 05 here. It's a jittery, awful nightmare. So let me stop this. Good Lord, that's noisy. So we've got this jittery, awful nightmare. The stepper motor on there sounds like it's about to come apart. It's just absolutely horrid. And if we look at the scope here, we can see this is showing the step impulses, or the step pulses that are coming into the card. And if we look at the period on these step pulses, it's about 3 to 4 milliseconds. And if we pull out our manual here and we go to the waveforms that it shows us right here at the beginning, it shows us the step signal, the waveform that's coming in. The actual signal can't be any shorter than 10 milliseconds. And we're at about 3 milliseconds. And so it's actually a miracle that it works as well as it does, and it doesn't just crash. So it's a well-designed CDC drive. But this is the problem we've run into, because especially when you're dealing with old computers like this, sometimes you can only buy what's available, not what was right. And what was right was the CDC 9406 or the 9409 floppy drives. Both of those have a minimum step spacing of 3 milliseconds, but the 9400, which is what this is, and the 9404 have 10 milliseconds. But I don't know if there's a 9406 or a 9409 out there, but I do know that I've got a 9400, and it won't work with the FFC card. The FFC is sending signals too fast, which means this drive is unusable. It's a lot of work for an unusable drive. And that's exactly how I felt last night. And SJ Software sent me a message and he said, "Nah, bruh, I got this." And he is confident that we can essentially push an update to the microcode of the FFC card to get it to work with this drive. Because the FFC card wasn't built specifically for this drive, it was built to be generic, to work with a multitude of drives. And the microcode was written to be specific to a 9406. So all we have to do is do a little rewriting of the microcode to make it specific to a 9400. And I am not smart enough to do that, but SJ Software is. And that's what we're going to dig into in the next episode. We're going to take a look at how we can update the microcode to get the FFC to work with this particular drive. Then we'll update the actual microcode, see if that fixes the problem. I don't know if it will. Hopefully it will. And then hopefully we can get deeper into it and start getting proper tests done. And maybe we can finally pass that read test. So we didn't get there today, but hopefully we're going to get there in the next episode. So I want to thank you guys so much for watching, and I hope to see you then.